Hi everyone, my name is Dimitri, and this is a bit of a, how should I put it, a bit whimsical webinar because we're not delving into the depths of science and whatnot. Instead, we're talking about random images, which is just something that I did for the fun of it and thought I would talk about. So the kind of stuff that we're going to be talking about is called generative art. That's when computers, as opposed to human beings, actually generate something that looks artistically pleasing, kind of like the image I'm showing right now. So this is, to me, it always seemed like a treasure trove of stuff that you can get for free and subsequently kind of print it and put it in a frame and hang it on a wall when you don't want to buy somebody's photograph or whatever. So, but this webinar, I'm going to talk about how these images are actually made and how we can speed them up. And I want to begin by actually explaining how exactly what is the process of generating these images. Now, I will confess that I'm not the originator of all of these ideas. These ideas for how you can generate stuff have been around way before, way before I tried to do stuff here. So instead of Visual Studio, I'm opening like a typical drawing application so that I can better explain the actual process. As you can imagine, what's happening with every one of these images is they're essentially generated by through random numbers. But instead of just generating random pixels, which would give us white noise, instead what we're doing is we're generating random functions. Now, the thing about random functions is that a function, well, first of all, let's try to classify functions. So, for example, we have unary functions, unary, and that's a function which takes just a single argument. So something like sine x, for example, that would take a single value. And then we have binary functions. So binary, for example, something like x plus y is a simple function. So you would have two inputs, x and y, and you would return x plus y. So out of these very simple building blocks, we can already construct something that appears more or less random, because let's imagine that we have a whole list of these binary functions. Let's suppose we have x plus y, and we have x multiplied by y, and we have x to the power of y, and so on and so forth. So we have several elements, and we can do the same for unary functions. So you can have sine, cos, exponent, log, whatever. So given that we have this set of unary and binary functions, what we can do is we can build them into a kind of super function. So if you think of it like a binary tree, where, for example, on top you might have addition, and down below you might have sort of another addition on the left, and something here, and maybe the sign of y down below, and here you would have, I don't know, maybe power function, and you would have things on the left and the right. So you get a tree, and this tree can be very big because it can it can nest, and as a consequence you end up with this rather large function of two variables. And why is it two variables? Well, because it makes it easy for us to iterate on the x and the y. So we can generally go through an image, and if you think of an image as a kind of rectangular grid of pixels, then we can take the x and y values, sort of, if I just render it like so. So for each point with coordinates x and y, what we can do is we can take the x and y values and feed them into this function. And for each of these, for each point on this image, we're going to get a unique value. And subsequently, we need to, well, first of all, we need to somehow make sure that the numbers we're working with are more or less sensible, because typically if you look at the coordinates of an image, let's say you have a 512 by 512 image, the coordinates would be from 0 to 511, but you can normalize them. You can just divide each value by 512, so you would effectively get a range going from 0 to 1, and somewhere in the middle you would have 0.5, and you would have 0.25, and so on and so forth, subdivided for each point. So a point might have coordinates, say 0.3, and let's say 0.6, and then you feed these values into the function. Now, for each point, you get a single value, And unfortunately, we need 3 values because, as it turns out, a single pixel is actually a collection of red, green, and blue values, effectively. So how can we go from a single value to a set of 3 values? And this is an idea that I've shamelessly stolen by somebody else who actually implemented another approach to this whole generative art puzzle, and this is to take a polynomial. So for each point in the image, we're essentially getting a single value. Let's call it z. So for a pair of x and y, we essentially get a z value. Now what we can do is we can generate a bunch of more random values. So we generate random floating point values for red, green, and blue, and let's just call them R1, R2, R3, and similarly we'll have B1, B2, B3, and G1, G2, G3. And then what we do is we take the Z value and we feed it into this via a polynomial. So the red, green, and blue values are calculated as, for example, Z squared times R1 plus Z times R2 plus R3. And the same goes for the green and the blue values as well. So this lets us take a single scalar value and basically turn it into R, G, and B components. And that's what makes the images so nice and interesting. Not my idea, but it's an interesting approach and it works. So having said all of this, we can jump into C++ and actually look at how it's implemented. And I want to begin by looking at let's jump into functions.h. So this is an illustration, if you will, of how we can approach this. So what we do is we type def 2 types of functions. So we type def a function of 1 float value returning a float and 2 float values also returning a float. And these are unary functions and binary functions respectively. And what we can do is we can initialize these vectors with just about anything that comes to mind. And I mean, my selection here is that for the unary functions, I went with sine, cos, the exponent, and the hyperbolic sign as well. And for the binary functions, I just went with a sum, the difference, and multiplication. And you'll notice I am using some adjustment factors here because essentially what I'm doing is I'm feeding this large function a range from 0 to 1. So now that we have a set of functions to pick from, what we need is to implement the concept of a random function. So we want to build a really large tree of functions which are completely random. So here is exactly that. So the random function is a tree whose nodes can be of 4 different types. A node can either be a unary function, which takes a single value. It can be a binary function. It can be just a terminal index, meaning that we're simply taking the x or y value that is fed at this particular point, or we have a terminal value, which is just a random value that we generate. So what we do now is we make a constructor for this random function, and we say, well, can you please tell us what is the depth of the tree that you want to manufacture? And based on this depth, we perform a recursive procedure where we build up this large tree, and you'll notice that there are pointers to the left and right hand side of the entire thing. So essentially, we essentially, while depth is greater than 0, we keep going and we build this function. And there is a bit of randomness in here in the sense that we're using a random value to determine, first of all, the kind of node that's going to be on the end. And ultimately, we also pick the randomness of the function. So we look at the total number of functions and we say, well, in this case, the index, that's the position of the function that we're going to call, is going to be determined by rand percent unary function count. Now you're probably wondering, well, why is he using rand? Not exactly modern C++, but RAND works here, and one of the reasons to use RAND as opposed to some of the more complicated stuff like, I don't know, Mersenne twisters and all that is that RAND is repeatable. And repeatability is very important in the whole generative art business. Let me explain to you why. You'll notice that most of the images that I've generated here, they're 512 by 512. Now, the reason I make the images so small is that I can view them and see which one is good. But when it comes to actually printing something and putting it on the wall, I want it bigger. And that's why repeatability using the same random seed that we started with is important. So this particular image, you'll see it's 4096 by 4096. It's big. And the reason I was able to do that is, first of all, I generated a small image, and then I regenerated it at the resolution that I wanted. And by the way, just in case you haven't figured it out, these images have no resolution. They have infinite resolution, in fact, because for the most part, if you're using smooth functions, which don't have any, discontinuities or anything, then the resolution of the image can go to infinity. It will always be smooth and beautiful, and this is why it's great. Because I mean, no matter how much money you spend on a digital camera, you're still gonna have a limit in the resolution that you get from your shot. Whereas here, there is no limit. If you want to build a picture the size of a wall at 300 dpi, then you can do that. So the random function is essentially a very large tree, and the only thing that we care about is actually evaluating it. So at each point in our two-dimensional space, we just feed it the x and y coordinates, and we get an evaluation. So the evaluation itself is actually fairly simple. If we let's just ignore all the optimizations here. I'll talk about them in a moment. But essentially, it's a loop where for each of the x and y points, we call the appropriate evaluation function. And this function is actually, if we just jump to it for a moment. So this function essentially does the actual calculation. Let's continue on this tree here. So if it's a unary function, it calls the unary function at index with the left subtree evaluated. If it's a binary function, it evaluates both the left and right-hand sides of the tree and then calls that. If it's a terminal value, it's just a known value that we already saved. And if it's an index, it takes it from parameters. The exact way why we're doing it like this, why we have vectors as opposed to just having x and y, is to do with vectorization, and it makes it easier when we come to actually talking about that sort of thing. So essentially, we're evaluating this rather large tree at each particular point, which immediately gives you a hint that lots of optimizations could be done here in terms of performance, because this is a computationally intensive task. It might not be so computationally intensive for a single image. Like, for example, let me show you how this is actually done. So the image gen, and if I specify, let's specify the dimension as 512, for example. Well, it's not particularly fast, but it's not critical. It's going to do it within reasonable speed, hopefully. or I might hit some sort of demo effect, and then it's like the whole thing crashing and whatever. But let me just let me show you how the program is set up. I will obviously publish the actual source, but essentially what I have is I'm using boost program options here, just in case you're wondering, and I have a number of arguments for how we can actually how we can do the thing with the configuration of the image that you're actually getting. So essentially, in terms of the kind of things that you can do, you can define the number of images that you want to generate. And this is kind of important because typically, if you generate just one or two images, most of them will be boring. And the more you generate, obviously, the better your results might be. In addition, we have a definition for function depth, and I think that's why it was slow, because I typed in a wrong thing. I typed in ridiculous function depth. So the argument that we want is, let me just dash. The argument that we want is the size, so that's Z. So if I do a 1024 by 1024 image, this is how long it takes. But that was a particularly silly image, you can see that there's only one unary function here that took an argument, even though by default we take a function depth of 6, but through randomness it can become a very small function, because we don't put any limiting factors on when you can sort of cut the tree by not putting a binary function in there. So here is a better one. Here's how long it took. Not that long, to be honest. So we're okay for the most part, unless we're building it at like 4096, for example. Let's try that just for the fun of it. 4096. Let's see how the whole thing looks. And by the way, my colleague is saying that somebody's asking about the structure window. Let me do that very quickly. So here it is, the file structure. Let it just populate a moment. And meanwhile, let me show you the So for those of you who don't know, the structure window just visualizes the structure of the file you're in, and it does all this kind of nice. Here is your struct, and here are all the members and all the rest of it. And by clicking it, you can actually navigate to the appropriate elements. But anyways, the whole business, well, it's done generating, and you can see it's generally okay for single images. You can more or less live with it. You might even live with it on a mobile device or a weaker device. But imagine what you can do with this, because in addition to making static images, you can actually kind of filter one of the parameters through a set of values and effectively make your own animations. And that's where the computation speed becomes really important. But anyways, we have this rather well parallelizable definition for how we can generate an image. So let me show you some of the code for how it's actually done, and there is plenty of stuff going on here, and you also notice that I have all sorts of optimizations all over the place. But essentially, it all starts with a seed. So the seed is a single, just one. There is just one random value from which the entire image is produced, and that includes those coefficients that I mentioned when I did the funny image drawing. These R1, R2, R3. They are also manufactured as a byproduct of that initial seed by using rather old C-style deterministic. Well, deterministic in the repeatability sense. So once you initialize the seed with a particular value by calling the srand function, then you can subsequently call it with that same seed again, just re-rendering it at some insanely large resolution, thereby getting your wallpaper or whatever. So what do we do? Well, we initialize a random function, just like the random function that I've shown you previously. There are some other parameters here that are a bit more advanced, but the point is, afterwards, once we're done with all of this, we simply generate the space of x and y coordinates, and we feed it into the random functions for a certain number of iterations. And this is another point that I think is better explained by drawing something. So let me, this is yet another idea that I stole. So essentially, the way that you can make the function even better is if after you calculate the value, after you calculate the z value, what you can do essentially, you calculate this set of r, g, and b values, but instead of assigning them to the image, you do a plus equals. So for a particular point, you say this point's red value is this point's red value gets added this red value, and then you can generate yet another set of these another set of z values for x and y, and you can add them again. And the thing is, when you generate it once again, you might have them generated with different coefficients. So as a consequence of that, it might be an even more interesting image, shall we say. And you can do as many iterations as you want. I think my default at the moment is 2. So that's something that you can control. In fact, it's another argument in the overall system. If we look up above, you'll see that the default number of iterations is 2, but you can change it to practically anything. So after that, the only thing that we have to do when we get the final values is we have to constrain them somehow, because if you think of a function, it's very difficult to keep it within the sort of, let's say, the 0 to 1 range. And even if you do keep it within the 0 to 1 range, you might want to, well, some of the values might go outside this limit. And I tried implementing all the functions in a way that they don't allow you to go too far outside the constraints of like 0 to 1 range. But in fact, it's easier to allow them to do so and subsequently just normalize the image. So that's exactly what I'm using. And afterwards, all I'm doing is I'm just saving the data, and that's pretty much it. Now, of course, if you want to render more than one image, you might have some sort of parallel implementation, and this is where I guess we can start talking about the parallelization efforts, because there are lots of places where you can actually implement multi-threading. The most obvious, of course, is right in the random function. So when you go through the sets of x and y values, all you can do is you can just drop a simple OpenMP pragma OMP parallel 4 here, and that will parallelize the loop. In a similar fashion, if you don't like the OpenMP variety, you could use something like threading building blocks or the parallel patterns library. Just make the loop parallel. And here, because of the way that the whole thing is structured, there is really no benefit in further customization of this pragma here. So no point in adding any additional arguments. And having two pragmas, I don't think will both inner and outer, I don't think this brings any tangible benefits. So there is really not much point in that. Of course, what you can also do is you can parallelize at a higher level, and this is what we're doing right here. So we put a parallel for each of the images that we're actually generating. Now, this is another fairly valid approach to doing things, and if somebody requested more than one image, then that's okay. I have a couple of different main functions here, by the way, and we can talk about those, because at the moment we've been using an ordinary main function, and all it does is it parses the arguments that using boost program options, and then it goes through each of the images to generate it, renders the image, and just saves it to PNG. That's it. Nothing particularly exciting. But in addition to that, what you can do is you can, for example, animate the image and end up with a video file. I'm going to I'll pop it up on a separate screen and show it on a subsequent just in a few moments, because well, it's actually 4K, and I'm pretty sure it's not going to load fairly quickly, so I'll save you from that. So my first approach was to just start parallelizing things, but then I was thinking that, you know, for each of the points, let's get back to the drawing board. So for each of the points, like this point and this point and this point, we're effectively computing the same function. So what if we were to grab the arrays and attempt to actually vectorize the whole process? And for that, I decided to use the Intel Math Kernel library. Now, the thing about the Math Kernel library is it's just like an ordinary math library, in that ultimately what you have is you have a function like sine or cos, but there are a few differences. Let's take a look. So essentially, the entire difference is, instead of sine and cos, you have vs sine, vs cos, and whatever. So instead of taking a scalar value, what you end up taking is a pointer to an array. So a unary vector function, as opposed to just a unary scalar function, would actually take the inputs as arrays, so as pointers to the first element, and the same goes for the binary function. And of course, given that you take this approach, you now have to effectively rewrite the way that you invoke this, because for a kind of scalar function, you just feed it two scalar values, x and y, and you get your end result. But for this approach, what you have to do is you have to prepare your arrays and then call them. And by the way, it's very easy to get sort of some of the, let's say, some of the Math Kernel library functions. They're easy to add to this vector of unary vector functions and binary vector functions. However, if you want to make your own function, it becomes a bit more tedious, because what you essentially have to do is you have to make a temporary array, and then you call your vectorized functions like vs_mul, vs_sine, and then you delete your temporary array, which is, you know, not very convenient, but that's the only way that you can go about doing this. So the whole purpose of this vectorization is to essentially leverage those SIMD instructions. So, streaming SIMD extensions and AVX and that sort of thing to get it, to get support for it. You can get it automatically from the compiler to some extent, but I always prefer, let's say, the more deterministic approach, which is why the math kernel library specifically. I mean, if we just jump here for a second, I'll show you the setting in the Visual Studio project. I think it's Intel Performance Library. So the use of Intel Math Kernel Library, you actually have three options here. You have the sequential option where nothing gets it's just sequential. You have the parallel option, and you also have the cluster option. So it's a rather sophisticated kind of library because it can actually leverage your it can basically piggyback on top of your cluster infrastructure, on top of MPI, and we'll talk about that as well because that's something that I tried next. So the whole point of doing the vectorization, the changes that you have to do effectively are as follows. Let's take a look what the difference is. So the random function that we have has a flag called vectorize, and if you set it, then instead of using ordinary functions, it's going to use those vectorized functions. So the unary and binary functions count will be taken from the vector functions as opposed to ordinary functions. And then let's take a look at the actual evaluation because that is the interesting part. So let me just let me find the exact approach. So here is the thing. We have a function called eval, and eval takes a width and a height of the image, and it takes a set of x and y vectors, so pointers to const float, so arrays essentially, and there's also an array for the result. And if we want to vectorize, then we have this special function called eval vector, and this function is different to an ordinary eval because essentially what you're doing is you're constructing a mesh grid, and those of you who are familiar with MATLAB might know about the mesh grid command. So essentially, it does an XY grid where each position has the x and y coordinate, and then you call yet another eval vector where using these prepared arrays, what you effectively do is you set up new temporaries, and then you perform once again the recursive calculation. So in like, for example, let's take a look at how you would evaluate a unary function. So you would go about and first of all evaluate the unary the left-hand side of the tree, but notice that the result of that evaluation gets placed in a temporary, that temporary that we've just created. And then, and only then, when the temporary is done, you can feed that temporary into the actual unary function. And because it's a vector, it automatically leverages all this wonderful parallel infrastructure. And it's kind of an additional benefit in terms of performance and in terms of just figuring out how this sort of thing operates. Now, it does become a bit inconvenient at some point to have to make these kinds of temporary functions, because remember, if you're doing it in a kind of scalar case, all you have to do is put in a lambda, and you put something inside that lambda. For the most part, I'm actually I think I'm doing too much in lines like this one, because instead of this, I think what you can do for the most part is just push back. I think you could just push back xf, just like that. I think that's a lot simpler. But if you do need to perform some sort of normalization, like for example, if your x value is from 0 to 1, you can multiply by 2 pi, and you can do a lambda and feed that lambda in. Unfortunately, in the case of vectorized functions, it becomes a bit more. So you do write a lambda, but unfortunately, you have to make this like temporary array, and you have to delete it afterwards. So it does get a bit more involved. All right. So next up, after the sort of both the OpenMP-based parallelization as well as this kind of vectorized approach, I thought about, well, what else can we do? How can we get it even at a larger scale? And of course, the solution to that is some sort of cluster build construct like MPI, for example. So with that in mind, what I decided to do is to go for MPI. And you'll notice that I'm using the Intel C++ compiler and consequently the Intel libraries and the Intel optimizations as well. So those, all that support for AVX and whatnot, this is something that you get the most of when you're using the Intel compiler. And I generally cannot recommend the Intel compiler generally, because the issue is that if you're after the latest and greatest C++ features, if you're after the best kind of stability, and if you don't want to see just error 3 and that's it, no explanation as to why the compiler just crashed, then maybe the Intel compiler is not for you. However, the real benefit here is that when it does work, it works with optimizations. It works in terms of being very fine-tuned for the whole business of using SSE and AVX if you have it as well. So, and I'm talking about that not just in terms of the math kernel library functions. I'm talking about that in terms of just parallelizing and vectorizing your loops without you even having to do anything. So if you set, for example, the parallelization setting in the compiler, what it does is it will use OpenMP on your loops even if you don't have OpenMP directives in there. So that is something to kind of watch out for. So I promised to show you an animation, and this is a 4K animation in actual fact that I did with this setup. So essentially what we have, this is just a 4K image where I'm manipulating one parameter and I'm getting the image to kind of warp from one side to another. There's nothing particularly magical here, but as you manipulate different parameters, you can get very interesting kind of results. I'm still experimenting with this whole thing myself, and after I publish the source code, maybe you can help me experiment with it as well. So the whole business of MPI, let's talk about that. So MPI is essentially a framework for running something across a cluster of machines. So it's when you have lots and lots of resources and you want to sort of spread out the execution. In fact, in the C++ world, we kind of encounter the whole distributed business a lot more than other people, because, well, for example, if you think about compilation, if you think about how long the program takes to compile. By the way, you'll notice that I'm deliberately not compiling this program in front of you, because since the program that we're looking at right now uses everything in the kitchen sink, including, as you can see here, standard library, as well as plenty of boost headers and math kernel library and OpenMP and library for rendering PNGs and whatnot. This takes an insane amount of time. So we use parallelization anyway. Like, for example, I've got Incredibuild, which is excellent for distributed compilation. Still, even so, the single translation unit here takes a lot of time. The building of the precompiled header takes up so much time. So, anyways, where cluster-related technology is where C++ feels at home. So let's take a look at the MPI variety of rendering. So the idea with the MPI renderer is let's first of all talk about what MPI is. MPI stands for Message Passing Interface, and it's essentially an old, and by old I mean like ancient. It's an ancient technology for cross-process, inter-process communication. So you can think of this image gen program firing up on not just a single machine, but like a dozen machines, and then those machines can talk to one another. So essentially, it's a communication protocol of sorts. And this communication protocol, initially, if you start using it, it has a kind of C-like interface, and it's not very user-friendly. However, we turn to Boost, and Boost is fantastic because it gives us a kind of wrapper around MPI. Unfortunately, you have to, it's actually quite involved, because Boost does not build MPI support by default. You have to configure Boost and build it to deliberately support your MPI environment, and there are different MPI environments out there. If we go into, I think it's, let me just check where it is. It's going to be a lot of fun now using, oh, here we go. So there are different MPI, for example, using the Intel MPI, but there is also the MPI Chameleon, and there is some Microsoft MPI applications. in this case on Windows, runs a Windows service which acts as a daemon, which actually facilitates this whole cross-process thing, essentially. So Boost does it essentially provides you a wrapper around the MPI environment and different calls to MPI. So what happens in the case of an MPI invocation of this whole thing? Well, the way I typically set up is that one of the machines sits there and just waits. It waits for somebody else to send it some render data, and by render data we mean the image as well as the seed that generated the image. Remember, the seeds are very important because if we have a seed, we can regenerate this beautiful image and get it, at a huge resolution. And in fact, in addition to just getting it at large resolution, what you can also do is you can take kind of define the x and y coordinates of the snapshot of that image. Because if you look at the images that I've just generated recently, you'll see that, for example, this image is a square. So what if you want to re-render it in like a 16:9? You no longer have the luxury of taking your coordinates going from 0 here to 1 here. You would have to have the coordinates scaled accordingly. And there is provision for that as well, because if you look at the one of the arguments that I'm using, the f argument is actually the frame. So you can define the minimum and maximum x and y coordinates, and this will generate based on the data. And one of the neat things this allows you is to pick out elements out of an existing image and render just those elements to an insane resolution. So for example, coming back to this image, let's suppose that you want just one of these little swirls in an image. What you can do is you can define your coordinates so they encircle only one of these elements or even inside the element, and you can render that. And I'm sure that at least theoretically, you could also rotate the image and sort of get these elements in a kind of orthogonal way. A bit more difficult perhaps, but certainly possible. And once again, and I love stressing this, it's all resolution independent, so you can get it to like any resolution that you like, almost. So let's get back to the idea of MPI overall. So the idea is that we have a single node which just sits there and waits and engages all the other processes on the different machines to actually send the data back. And then what happens on the other machines is that we simply render the image, and you'll notice that the image rendering options that we're using here, they are actually parsed from the AC and AV arguments. So it looks like I did a few overrides here because maybe this seed was particularly important to me. So you basically, on each of the nodes, on each of the computers on your machine cluster, you would basically render the image, and then you would just, instead of saving it to a file, you just send the data back to the original node, and then the original node kind of builds the file name and saves the image. And you'll notice also that when building the file name, there's only one important thing, that is the seed, but I also had the width and the height. But the seed is critical because what I can say is, by the way, let's suppose that, for example, I want this image. Now what I can do is I can just copy that part of the name. So I can copy the seed here, and then I can go back into the console, and I can say, okay, so image gen, I want to take the seed that I've just saved, space that, and I want to render it at, let's say, 2048 by 2048, something to that effect. So I fire this up, and it does take a bit more time, and then we can go back, and hopefully once this is done, we'll get to see the updated image. Here it is. It's still rendering the preview, but if I double click it, well, it looks like the same image, but let's look at it in native size. So you see it's much higher resolution. So that's how you can sort of regenerate things and at whatever resolution you effectively want. So MPI is extremely simple to use and to understand, and there is no particular issue with MPI as such. The only problem is that you have to set up the firewall. That's one of the problems that I personally hit when communicating between different machines. Of course, in my case, what happens is I use a cluster which uses scheduling. So I cannot show this in real time because you effectively submit a job and then you wait however long you have to wait. But when when you're done waiting, essentially what it does is it returns you like 100,000 images, and then you can sift through those, and you can. I think I've been collecting well, some of the images that we actually used when we were advertising this webinar were images that I was collecting in the process of iterating on this design, and certainly the set of functions that I was using for rendering it does change. So I don't even have the seeds here to regenerate these images, but as you can see, these are some nice images. They're kind of like if you, for example, if you want to do abstract packaging, if you want to like design a bag, but you don't really want a photograph on it, you just want something that looks kind of weird and funky, and you don't want to pay anyone royalties for it, so to speak, then these are some of the images that you could use. And something like this, for example, is a postcard type image. So I'm making postcards. Maybe when I retire, I can use this this program to make and sell postcards of little hearts on pink. I'm sure that would make a lot of money. So yeah, the MPI is, I guess, the pinnacle. And obviously, the great thing about all of this is that you can combine the approaches. So at the same time, you can pretty much get all the benefits. You get the benefit of streaming SIMD extensions or AVX if you've got support for that. You get the benefit of multi-threading, which is very easy to leverage, because I mean, well, it is easy in this case because the iteration on X and Y is a fairly obvious construct. So that is some of the approaches that you can take. And on a higher level, what can you do? Apart from MPI, and MPI is something that is I'm sure kind of self-explanatory. So you run a process on each of the machines, and therefore each of these processes gets to leverage vectorization as well as multi-threading as well. But in addition to that, you can do some other things, and I will put those as additional source code as well. But you can do things like run on a GPU, for example, because this entire thing, I mean, this function that we're generating, this random function, can actually be generated statically. And what you can do is you can grab this function as text, and you can effectively compile it at execution time. And I'm not joking. Let me just briefly show you what it would be like to do so. So let me go into projects. This is related to an entirely different demo that I have of different CUDA implementations. But what you can do is you can generate. Let me just see where the syncs here. Nope, not the right one. What you can do is you can generate this function not as a tree, but you can generate it as source. And this is something entirely different, because what you would effectively be building is something like this. All right, so what's going on here? Now, this is also a random function. Here it is. I'm not kidding. It's a random function, but it's written in text. So what your generator would do, instead of having it as a kind of a tree inside a RAM, basically, what you would do instead is you would have the function defined as text as part of a GPU kernel, and this is a fully fledged CUDA kernel. This is something that you could compile, for example, and if you compile it at execution time, you might, for example, get a PTX, so you might get a file like this. Don't worry, I know it looks like assembler, and I guess it is assembler for the GPU, but the great thing about this is that you can subsequently load it on your GPU at runtime. And as a result, you can also generate images in pretty much the same way as we're doing here. So that's one possible extension. Of course, other possible extensions include, for example, if you have a Xeon Phi device, then you can just keep using MPI or OpenMP, because for a Xeon Phi device, it doesn't really matter. And I guess the pinnacle of all of this would be somehow hard coding this thing into some piece of hardware. And I've actually, and this is one interesting approach, you can now buy these little computers that plug into the HDMI port of a television. So you could take one of these little computers, put this little program on it, and stick it in there, and it would feed you random images or whatever you want using the algorithm like this one. So obviously, since I'm slowly running out of time here, I just wanted to say that the set of functions here, you can make a huge set of functions and get really strange results, or you can totally ruin the game. How can you ruin the game, you might ask? Well, for example, let's imagine if we had x divided by y, then anytime that y would be a 0, you would get an infinity. If you have if you have a square root, what would happen with the square root of -1? It's not suddenly going to jump into the complex plane. And in fact, even though it might seem a bit off tangent, but doing it with complex numbers is something that I would want to do. Quite frankly, that's what most people do, because, well, what kind of generative art do we all know and love? Of course, it's fractals, and fractals are done using complex numbers as opposed to ordinary numbers. So that's a possible extension for the overall model. So this is, I think, pretty much all that I wanted to say in the time allotted. I think it would be beneficial if you check out the actual source code. Maybe we should, like, I don't know, set up a website where people can post their creations or something to that effect. Although I have to stress that there is nothing particularly magical, and the approach that I've shown here is just something that I've once again, I saw other people do, and I got jealous because somebody in particular, they posted their beautiful images without sharing the source code, and I thought, well, how about sharing and then I built it myself, of course. And I don't know how well I did, maybe not as well as they did, but it's certainly a start. So having said that, I want to thank everyone for checking out this particularly weird webinar. Let me just check if there are any questions in the question thing, because I've been ignoring it for the entire
with the questions. So just first of all, thank you for presenting. It was really very interesting and
isn't RAND considered harmful? Yes, RAND is definitely harmful. The okay, so I don't know if the Mersenne twister is repeatable. Certainly something from the random header that is a repeatable sequence should definitely be used. However, you have to realize that this particular application, the application that I've built here, is not really sensitive to the quality of the random number. So we're going to be okay for the most part. If Mersenne is indeed repeatable, then that's okay. But we might switch to that as well. Okay, so why row pointers instead of std array, std vector? It's just a kind of I do this automatically because my brain evaluates the level of complexity, and it says, well, can you manage this? Can you manage, like, destroying the right and left leaves of a tree? And the answer here is yes. The answer here is that I can in fact do that. Yes, OpenMP does have issues with unsigned iterator loops, and it's not just OpenMP. You know, the things that annoy me is, like, for example, C++ AMP, which also has these silly restrictions on the kind of types. Like, for example, in C++ AMP, you can only use integer types. You cannot use, like, a short or an unsigned char, and that's annoying because you've got a GPU, and let's say you want to do some substring matching or something like that, and you cannot because it's simply constrained in the following fashion. So it seems that parallelization can be extended to the use of OpenCL rather than the I mean, you could use some other framework. You could use C++ AMP, you could use OpenCL, or indeed CUDA. And I talked about CUDA. I guess CUDA and OpenCL are kind of counterparts. I think the whole, I mean, for me, I intuitively jump to CUDA because I know it better, but that's not really an excuse. I do find OpenCL a bit more verbose overall. It does require a bit more writing, but then again, OpenCL is the kind of technology that tries to be all things to all people, so it tries to encompass all sorts of devices, whereas CUDA does not even it does not even have a decent well, I don't think it has any emulation in x86, so it's only, please debug this on a real device or else. This sort of thing. CC cache on Linux would be magic to reduce compile times. Lots of things are magic to reducing compile times. My personal approach to fighting compile times is Incredibuild, which I guess until recently it was Windows only. Now I think it also supports Linux in some capacity, though I haven't tried it. There is also something called FastBuild, which is another distributed compilation thing that's actually free, because typically these things, and certainly Incredibuild and Electric Cloud and others, they're reasonably expensive, I would say. So FastBuild is one alternative. Of course, we're all waiting for modules. So given that Anastasia and I are flying to CPPCon soon, we're hoping for an announcement of modules in some capacity. I mean, who knows? It might happen. And I'm sure many of you saw that funny video with a certain German discussing the lack of modules in C++. Personally, yeah, I think this would be a deal breaker if we finally got them and we finally cleared this issue once and for all. One thing I realized, and I had this idea that if you use precompiled headers, then suddenly some magic happens and you only have to compile once. Unfortunately, with the Intel compiler, it seems like your precompiled header is rebuilt on every build. So I can't say why. I've already started complaining to people, but maybe it's a limitation. And it's a really annoying limitation, because that's why I haven't rebuilt the project once during this entire demo, because it would rebuild the standard AFX.cpp, and that would just take too much of your time. Yeah, we may as well create a Flickr group or something like that. Hopefully Anastasia and I will agree on some sort of format, and you'll get the source code with the functions that I'm using here, and you're welcome to add your own functions and constrain them. Let's see, do you have some performance measurements comparing the various implementations achieved, OpenMP vectorization, CUDA, and MPI? I do, but they're not particularly scientific. So OpenMP does a pretty much linear increase, because that's how multi-threading works compared to single threading. The only difference, the only problem why I struggle to compare it directly is because in the Intel compiler, you turn on parallelization, and suddenly every single one of those loops that you made is using OpenMP anyway. So it's very difficult to diagnose where you actually added a particular element. So vectorization in this case was not particularly effective. I would say it gave an increase of less than 2, which is bizarre. But also one thing you have to realize, and I keep telling it to people all the time, is that when you use vectorization, your results, your numerical results, the results of your computations will not always be the same as the results of non-vectorized computations. And in some cases, the results might diverge in a crazy way. Why this is relevant? Well, because in our case, we have very deep nested functions, and these divergences can get quite big. In fact, let me see if I've got the code here. I used to have this chunk of code where I explicitly compared, let me just open up the list of functions here. I might have deleted it, but I have this equivalence check. Yeah, I think this is it. So if you go through, so I think, here's what I did. I took a random function and I evaluated it with vectorization and without vectorization. I did it a few times, and in certain cases, you see really crazy differences. And I'm sure you can realize why those differences are. That's because of associativity. It's a simple byproduct of mathematics. The fact that A times B is not necessarily B times A. Sorry, but that's the way it works. Regarding CUDA, I have not performed any comparisons. However, in addition to this project, I will post the CUDA project as well. There is an issue with CUDA which prevents me from showing it today, and that issue is that the computers where I have my NVIDIA cards are high DPI. And the funny thing happened with high DPI just recently. I launched my CUDA projects and I was going to show it today, but then all my images were broken. And the reason why images were broken is because I'm actually rendering those images via .NET, of all things. And it seems that something is broken in .NET on high DPI monitors, because I make the bitmap object in .NET. I feed it to this image generator. I get it back. I feed it to the CUDA generator rather. I get it back and I get noise. It's just junk. I don't know exactly what's going on there. Maybe it's some sort of high DPI interaction that's actually changing the DPI settings of the bitmap or something. But I need to fix it. So I couldn't figure it out. But CUDA should be. Here is the problem with CUDA. Why can you not compare the performance of CUDA. And the reason why you cannot compare the performance of CUDA is because compilation of the kernel is an operation that you have to measure. So this CU kernel that we've built, I mean, we build it as text. We save a file. That's okay. That's easy. The problem is that at this point, and I don't know if there is some in-process way of doing it. At this point, I'm calling literally an out-of-process batch file. Let me show you. I'm calling no, don't. Okay, just one sec. I pressed print instead of just editing it. Let's try this again. Let's go to edit. There we go. So as you can see, what I'm doing here is at some point, and I'm doing it through a C++, just a function call, but I'm calling the NVIDIA compiler on this particular kernel that we've generated at runtime. Here it is, temp.cu, and I generate the PTX for it. So this operation is not exactly fast, as you can imagine, because, well, you're calling something out of process and you have to wait for the NVIDIA compiler. So it's not really something that you can even affect. Now, maybe there is a way of in-process compilation, but I don't know about it. So we'll have to see. And obviously, when we're talking about MPI, the speed up is more or less linear, because you can consider the time that these images spend on the wire to be virtually zero compared to their generation time. So in terms of MPI, you know, it depends on how many machines you have. And I have a few, so that's that. All right, so that's 1 hour of me talking about images and how wonderful they are. And once again, I thank you for joining this little webinar. Anastasia, do you have anything to add or comment?
Yeah, so I'll just share a couple of useful information just for a couple of minutes. So just feel free to provide any feedback on the webinar, or just any feedback you have to Dmitry or me via Twitter, or you can ping me via email. And if you'd like to know more about C++ tools from JetBrains, including CLine or resharper-C++ Dmitry were using today, just go to jetbrains.com/cpp or follow us on Twitter. So as we said, the video recording on the webinar will be available in a couple of days, so I believe tomorrow or on Monday, on our YouTube channel, and we'll announce there all the social media we have and in blog. So, and thanks everyone for joining us today. If you'd like to learn more about upcoming webinars, just subscribe to our Twitter. We'll be happy to have you next time for the webinars. So thank you, and develop with pleasure.
Thanks a lot, everyone. Bye-bye.
Yeah, bye.